Do you like to do awesome stuff? I like to do awesome stuff. Let's do something awesome. We can look at the motion of an object near the Earth, orbiting the Earth or whatever you want. But we can only do it easily for the simple case of circular orbits. But what about non-circular orbits? How can we do that? We are going to build, I'm going to step you through all the things you need to do to build a 3D model in Python for an object moving near the Earth, not circular orbit. But let's start off with a circular orbit just so we have a baseline to start with. And then I'll go through all the physics and all the code. It's going to be awesome. Okay. So we have the Earth right here and an object moving in a circular motion with some velocity v with an orbital radius r. And I have the parameters for the mass of the Earth and stuff like that. Doesn't really matter. We can use this force, the gravitational force between the two objects, to look at the motion. Now, if it's moving at a constant speed in a circular motion, then F net in that direction, I'm going to write this as a scalar, is mass times acceleration, but the acceleration is the acceleration of moving in a circle, which is mv squared over, I'll call it lowercase r. Then if I put in my only force, the gravitational force, g, mass of the Earth, mass of the object over r squared is equal to the mass, v squared over r. The mass of the object cancels. I'm going to solve for v squared. V squared equals g, mass of the Earth. One of these cancels with that over r. So v, the velocity for circular orbits, is the square root of g me over r. So I can pick a value for r. I can find out the initial velocity and it'll move in a circular orbit. Let's just write that over here because we're going to need it later. V, I'll call it v circular. Square root g me over r. Nothing new there. Okay. Now, what if it's not in a circular orbit? What if, in fact, it's over here and it's going that way with some velocity v? Well, that's a tough problem, right? Because if it's moving this way with the velocity v, a little bit later, let's say it's over here, and now it's further away from the planet. Not only did the magnitude of the gravitational force change, but the direction of the force changed. So it's a non-constant force problem. That makes this pretty tricky. Well, there are multiple ways to deal with this. There is a way to deal with this. It's called the two-body problem, but it gets pretty complicated. Instead, what we're going to do is to cheat. We can cheat by breaking this motion into a small time interval, delta t, and how small would that be? It's kind of hard to say right now because we're dealing with orbital motion. Let's just say 1 hour for now. We can change that. If delta t is 1 hour, then the distance this moves, actually, let's do 1 minute. We can always change that. 1 minute. In 1 minute, it's not going to move that far, right? So I can assume the force is constant. And if I assume the force is constant, then I can use some more normal ideas about changing the velocity of this object. Okay, now to do this, we're going to have to use different notation. We're going to have to use vector notation. Okay, so first of all, I'm going to describe the position of the object with the vector r. Now, in this model, I'm going to put the Earth at the origin. And you don't have to do that, but I'm going to do that just to make the code simpler. We can change it later if you want. So the Earth's at the origin, the center of the Earth's at the origin. This is at a vector location r. That's important. The velocity is a vector. Now, how do I calculate the gravitational force? I had this, m Earth, m over r squared, but that's not a vector. So I'm going to write the vector formula for the force on this using this vector r, and it looks a little weird, but it's important. It's not a big step. If you don't really understand this, it's fine. Okay. I'm going to write the gravitational force as negative g, mass of the Earth, mass of the object. I can't square a vector, so I'm going to take the magnitude of that vector squared. Now, that's not a scalar, so I can make it a scalar by multiplying by r hat. R hat is a unit vector in the direction of r. So in general, just say r is the vector rx x hat plus ry y hat plus rz z hat, right? That's how I write a 3D vector. The magnitude of r would be the square root of rx squared plus ry squared, I'm having trouble with my y's, plus rz squared. The magnitude, the unit vector r hat we define as r hat is the vector r divided by the magnitude of the vector r. So what that does is it makes a vector that has a length of 1, but it's in the direction of that vector. So since I know that force should be in the opposite direction, negative r hat will turn that whole scalar thing into a vector. I know that's a lot, but that's what we need to do. Okay, so we can calculate the gravitational force as a vector. What do we do with it? Well, how about this? I'm going to write that up here. So I have that. F negative g, mass of the Earth, mass over the magnitude of r squared, r hat. I can set that equal to mass times acceleration as a vector. So the acceleration I can calculate very easily. It's the same thing, it just, this mass is gone. Now with that acceleration, I can assume that acceleration is constant over my short time interval. That's going to be the change in velocity with respect to time. And now let's call this v1, and let's call this new velocity v2 as vectors. I can write the change in velocity as v2 minus v1 over delta t. If I solve that for v2, I get v2 v1 plus a delta t. And there is another way to do this using momentum, but I'm going to do it this way for now. So that's an important equation. This is an important equation. But now if I know the velocity, if I update the velocity, I can use that updated velocity to find the new position. So let's define the average velocity. We're going to assume it's constant, even though we know it's not. Well, I told you we're cheating, right? So you can't say, hey, you're cheating, because I already said we're cheating. Gotcha. The change in position with respect to time, and these are all vectors. Well, time's not, and I can write that as r2 minus r1 over delta t. The change in position. I can solve that for r2, and I get r2 equals r1 plus v2 delta t. That's an important equation. Now we're done. We have a way to find the new position and velocity of the object after some short time interval delta t. Calculate the force, calculate the acceleration. Use that acceleration to update the velocity. Use that velocity to update the position. Now, I have just found out where it will be after 1 minute. But if I'm orbiting the Earth, it's going to take 90 minutes, okay? Which means that I know that at low Earth orbit. I'm just going to leave it. So let's use a delta t of 1 minute for right now. But now I don't know how it is after the next minute. I have to redo this whole thing again. And then redo it, and redo it, and redo it. Nobody wants to do that, so we make a computer do it. And that's where Python comes in. So we're going to implement this method in Python, and we're going to make it 3D. So if you haven't done this before, hold on, because it's awesome. Okay, I'm going to jump over to Python, and let's work on that. So here we are. I'm using Web VPython. So Web VPython is Python online, the web. And the VPython means it has these visual elements built into it, and it has vectors built into it too. Let me just go ahead and write the simplest program. We'll run it, and we'll see what happens. So here's my code. I'm using trinket.io. I will give you the code. Don't worry about that. There. Okay. Sphere. Sphere is a built-in object in Web VPython. That's my whole program. Oh, the first line, Web VPython 3.2, that's for Trinket, so don't change that. Play. There's my sphere. So that sphere is a built-in object in Web VPython, and by just using that as my code, if I click and drag, you can see it's an actual 3D object, and I can rotate it and zoom in and out. So that's kind of awesome. Okay. So we can use this sphere object as our planet, Earth, and as our object. So let's go ahead and start putting in some stuff here. I'm trying to think if that's big enough. I want a little bit bigger. Okay, the first thing I'm going to do is enter some constants. G equals 6.67 times 10 negative 11th. I'm not going to put my units as a comment just because I want to go faster. Mass of the Earth, I'm going to call that ME for me. 5.972 times 10 to the 24th. It's 972, right? Yep. Okay. The radius of the Earth, RE, is 6.37 times 10 to the 6th. So I'm going to make the Earth. I'm going to make the Earth an object. I'm going to give it a name. I'm going to call it the Earth. It's an object of type sphere. Now, sphere also has some properties that we can give it. We can give it a position, we can give it a radius, and things like that. So let's give it a position as a vector 0, 0, 0. It's 3D, so we need 3 coordinates. The radius is RE. And that's it. I'm going to run it, and nothing's changed. Nothing's changed. Yes, the radius is 6 million meters, but VPython zoomed out to make it fill the whole screen. So that's that. Now, for the magic part. We could change the color of that, but I could also do this. Texture equals textures dot earth. So that's just a fun little trick. There are built-in textures that you can put on top of surfaces. So now I made this look like the Earth, and you can rotate it around. And this is so useful for a whole bunch of stuff. You could use it to make illustrations and animations, and I do. It's awesome. Okay, but now we have the Earth. Next, we need to make our object. We're going to call this, we could call it a spacecraft. We could call it a ball. I'm going to call it a ball. It doesn't really matter what you call it. Ball equals sphere. Now, where are we going to put this? I want to put this on the x-axis, which would be this way, a distance twice the radius. And I'm going to make the size, let's say, 20 times smaller than the Earth. So the position is going to be vector r 2 times re, 2 times re, 0, 0. And the radius is going to be equal to RE over 20. And then let's just leave it as the default color. No, I'm going to make it yellow. Color equals color dot yellow. And I'm going to run that. And so there's my object. Of course, it's way too big to be a spacecraft because if you make it the correct size, you can't see it. So I made it a lot bigger. And there it is, and you can zoom, see it rotates around. Isn't this awesome? We're having a great time. It's not just math, it's not just physics, it's art. Okay, now I am going to need I don't technically need a mass for this object, but I'm going to give it a mass of 1,000 grams. I'm going to call it M equals 1,000 kilograms, just for fun. I also need a time. Time equals 0, and a time step. And I said a minute, I'm going to stick to that, so that's 60 seconds. I need to actually do my calculations in seconds, because G is in seconds. And I need an initial velocity. I can't change the velocity if I don't know the velocity. So I'm going to give the ball a velocity, and I'm going to calculate what that should be. I'm going to say VC, the velocity moving in a circle, is the square root of G times the mass of the Earth divided by the radius of the ball, the orbital position of the ball, which is 2RE. But I'm going to show you a little trick, okay? I can actually reference the location of the ball by using its property. So ball.pos is the vector location. Now, I can't put that in there. So I actually need to take the magnitude of that vector. So I'm going to take the magnitude of ball.pos, and that's the position of the ball with respect to the center of the Earth. You could just put 2RE and you'd get the same thing. Okay, that's the velocity that I want to go with. Now I need to give my ball a vector velocity. That's just a scalar. I'm going to use ball.v for the velocity. So v, I'm going to associate it as a property of the object ball. You could just say v if you wanted to. I like doing it this way because it's better. So I'm going to, if the ball's in the x-axis, I want to give it a velocity perpendicular to that in the y-axis. So the velocity is going to be a vector in the y direction, vc0. Okay. Now, what do I need to do? Well, I need to do all the calculations that I said, but I need to do them a whole bunch of times. So I'm going to use a while loop to do that. So let's run this for 3 hours. Okay, so while, and we can change this later, t is less than 3 hours, but I need that in seconds. So that's going to be 3 times 60 times 60. That's 3 hours, right? Okay. Now the next thing that if you've done some of my previous tutorials on Python, if I'm making an animation and I want things to move and I want to display how they move, well, then I need to tell it how fast to redo each animation. So I need to give it a statement in here called rate. So rate, and yeah, I'm just going to put rate as 100. Rate 100 says don't do more than 100 calculations per real second. So I don't want it to run in real time because I'd have to wait 3 hours for it to run. So I'm just going to use 100, and we need to change that. We can. That might need to be, let's put that at 300. Okay, now we're ready. So if you look back up here, the first thing I'm going to do is to calculate the force. So the force is this equation. I'm going to just type it in here. F equals negative g times the mass of the Earth times the mass times the unit vector r hat. So let's put it up here just for fun. R equals ball.pos. It'll make it look a little bit nicer when we write that. So now I can take the unit vector of r that's a built-in function into Web VPython, and it's called norm r. If that doesn't make any sense to you, that's fine. Just understand that we need that to make sure our force is a vector. And then I need to divide by the magnitude of r, which is like I said before, built-in function, mag r squared. Raised to the power in Python is star, not hat. Okay, so that's it. I've calculated the force. Next, I'm going to calculate the acceleration. And again, this is kind of redundant. You don't have to do this. There's another way to do it, but A is F over M. Because I could have just calculated A, right? But that's fine. Now I'm going to update the velocity of my ball. Ball.v equals ball.v plus A times dt. So A is the acceleration, multiplied by the time interval, and then I'm going to change the value of the velocity. So this is a make equal to sign here. This says take that ball velocity, add this to it, and then set that equal to the ball velocity. So I don't have to worry about v1, v2, v3, v4, v5, 6, 6, on forever, just once. Now I'm going to update the position. I'm not going to update R. I'm going to just go ahead and update the position because I actually want to move the ball. So ball.pos equals ball.pos plus ball.v times dt. You could up here call this a ball.a, but you don't really need it. So now I need to update time. T equals t plus dt. And then I'll do it again and again. Let's run this. Let's save it. Don't you think I should save it? My first orbital motion. I just made that up. Save. Okay, I'm kind of nervous. When I run these things, you never know what's going to happen. Oh, it worked. That was pretty good. Okay, it went a little bit fast. Let's slow that down to 100 and run it again. Check that out. So the computer is going to zoom out a little bit to make it work. It is in a circular motion. Everything's great. Let's make it a little bit better. There is a property that we can assign to the object ball called make underscore trail equals true, capital T. So that's a property, make trail, and I'm just setting it to true. So now when the ball moves, it's going to leave a trail behind. It's going to look a little more awesomer. Check that out. 3D too, look, it's in 3D. Okay, so I didn't make it all the way around because I didn't run it for long enough, but it seems like I could do that. Let's run it for 6 hours. I just guessed. And let's see if it does make a complete circular orbit or not. Here we go. Okay, that's good. So that tells me that my time step was indeed small enough. You may have to play around with that time step. Those are the two things you're going to have to play around with. The time step and then the rate statement, right? Because you want to make sure it runs in a reasonable amount of time. You don't want to get bored or anything like that. So you want to make it run fast enough that you're not in real time. Okay, but now let's play around with something else. Let's give the ball an initial velocity so it's not moving in a circle and see what happens. Going back over here, I have the circular motion. I could do something like just increase the velocity. Let's do that. I'm going to make this 1.5 times the speed of circular orbit, but at the orbit r. So it's going too fast to be in a circle. Let's see what happens. Okay, that was a little too fast, I guess. So it's just taken off. Let me make that just 1.2. How about that? Okay, that's better. So you can see that it's not a circle, but it is moving around the Earth, and it's going to get back to where it was. It's going to make a complete orbit in a longer amount of time, but it's not circular. And that is something that would be very difficult to model if in just normal algebra. It's possible you can do this. Okay. Now let's give it an initial velocity like moving away from. Now I'm going to have it move like towards the Earth, give it a little component towards the Earth just to see what will happen. So let's say this is negative 0.3 times VC. So it has some negative X component and a Y component. And I'm just going to run it. Okay, that was probably a bad idea. Let's give it a positive. I mean, it's going to still orbit. It's just a bigger orbit. I'm just trying to play around with it and get some good things. Let's make that positive, see what happens. Okay, again, too fast. So let's make this 0.7676. Okay, this is good. That's what I want. Notice what happened here. There's two things that happened. One, it went through the Earth. Why did it go through the Earth? Because the Earth is not there. The Earth is just a drawing, right? I never told it what to do if you hit the surface of the Earth. I never said there was a surface of the Earth. And so Python's like, I'm just going to keep going. So it went through the Earth and got closer to the center. Notice also here that these don't line up. They kind of change a little bit. Why did that happen? Well, because as it gets really close to the Earth, the center of the Earth, r gets very small, the acceleration gets very large, and it actually moves too far, and it makes that approximation that delta t is small, not a great approximation. So we break our model a little bit here. I mean, it's okay in the end. We can fix it by just changing the time step to be smaller or giving it a larger velocity so that that doesn't happen again. Ooh, it still went through. Okay, let's get that a little bit higher. 0.9. Now, this is it. I'm done. But I'm going to tell you that we can check our calculations once we get into the ideas of energy and angular momentum. We can use both of those ideas to see if our code is giving us legitimate results. But for now, that's it. If you've done this, if you work through this on your own, play with this code, try your own orbits, do whatever you want, break it. Just so you know, if you ever break it and you go up here to click this, you can reset the code back to what it was because it's my code, or you can copy it and paste it as your own code, and you can change it whatever you want. So there you go. Orbital motion in Python. Hope you enjoyed that. I had fun. I'm going to put a link to that code so you'll have that to play with. But this is opening up a whole new world of stuff, right? Because you can do a whole bunch more stuff. And this is as simple as it can get. We can make much more complicated, but that's a great place to start. The end.